This is C2134 Group 7. I'm Reiko.
I am Qi.
I am Riley.
I am Si.
And I am Steven.
Have you ever thought about what happens when you flush a toilet? The flushing mechanism actually involves a fluid mechanics principle called the Bernoulli's principle, which I'm sure we all remember from this module. But we will dive into the equation and how these changes in pressure and speed cause the flushing effect.
Before we start looking at Bernoulli's equation, however, let's understand a toilet's main components. When the flush button is pressed, the flapper valve opens, releasing water into the toilet bowl from the tank. This causes the water level in the siphon tube to rise over the bend, and the siphon effect starts, allowing the water to be flushed into the sewage system.
This is Bernoulli's equation. It is a key concept in fluid mechanics that relates pressure, density, speed, and height. In this case, it helps us understand how the velocity of water changes as it moves from the toilet bowl down the siphon tube and into the sewage system.
For the toilet bowl, we have two main points to consider. The first point is inside the toilet bowl, right at the top of the water level, while the second point is at the end of the siphon tube, where water is pulled to and flushed away. Now, we will apply the Bernoulli's equation to the process of flushing the toilet. The surface of the water in the toilet bowl, denoted as point 1, will have a pressure equal to the atmospheric pressure, and this is an open surface exposed to the atmosphere. We will assume the initial velocity to be 0, as the water is close to stationary. And height is a variable which we will call Z1.
At the end of the siphon tube, point 2, the pressure will still be 1 atmospheric pressure as it is also exposed to the atmosphere. And the height is Z2.
As more time passes after the toilet is flushed, the water's velocity will increase due to the change in height, which is labelled as delta H in the diagram, and it will accelerate due to the siphon effect. To find the velocity at point 2, which is v2, we can input the known variables into the equation. For example, we know that the velocity at point 1 is 0, and we can cancel the common factors on both sides, like pressure and density. So this will result in the following equation shown on the screen. Lastly, we can make v2 the subject of the equation and solve it. Thus, the velocity at point 2 is equal to the square root of 2g delta h. Therefore, the difference in height in the Bernoulli equation creates a siphoning effect, allowing the toilet to flush with a velocity of square root 2g delta h. Other than flushing a toilet, here are some more real-life examples of Bernoulli's equation in action. The first application is a Bunsen burner. When you first open the Bunsen burner with the air hole closed, you'll notice it produces an orange flame. This is because only gas is flowing through. Now to create a stronger, hotter blue flame, we need to open the air hole. When it is open, gas continues to flow out of the nozzle at a high speed. This creates a low pressure zone inside the burner. Since there's higher air pressure outside, air begins to flow in through the hole, mixing with the gas. As the air and gas mix, the flame turns blue, signaling a more efficient, hotter burn. Secondly, the fine mist from spray bottles are also due to Bernoulli's equation. So in a spray bottle, when you press the spray button, air is forced over a small tube containing the liquid. So according to Bernoulli's principle, the fast-moving air creates a low pressure above the tube, drawing the liquid up, where it's broken into fine mist, allowing for a smooth spray. And that concludes our video. Thanks for watching and happy flushing!